On April 10, 2013, 165 million tons of rock collapsed into Bingham Canyon at nearly 100 miles an hour, burying 95% of the pit floor hundreds of feet deep. The largest mining-induced landslide ever recorded. To dig the mine back out, Kennecott did not send an army. They sent an 1,800-ton electric shovel and a single operator. The job looked physically impossible. This machine is the P&H 4100 electric rope shovel, designated simply as 99. Standing 6 stories tall, this 1,800-ton steel frame has the footprint and physical presence of a multi-story industrial building. At the front hangs a massive dipper bucket designed to bite up to 120 tons of blasted rock out of the earth in a single pass. Under normal operating conditions, this single machine runs for up to 20 hours a day, scooping up nearly 200,000 tons of material before the shift ends. Yet despite this colossal physical scale, control of the entire machine rests in the hands of one person. From a high-visibility cab ringed by reinforced glass and external safety cameras, veteran operator Randy Maguire guides the shovel's massive movements alone. Shovel 99 was built to dominate the daily production demands of a massive open pit. When the mountain collapsed and buried the pit floor, this machine became the only asset capable of digging the operation back to life. Bringing a machine of this scale into the pit is not a matter of driving it down the haul roads. Shovel 99 arrived at Bingham Canyon completely disassembled, packed onto 60 semi-trucks and 10 rail cars. A specialized crew spent 50 to 55 days erecting the frame, aligning its heavy gear systems and integrating the control systems on a wide bench within the pit. Once built, the shovel remains anchored. It does not run on a self-contained diesel engine. Instead, a trailing 5,500-volt alternating current cable feeds the electric motors directly from a fixed substation. As the tracks crawl forward at less than 1 mile per hour, ground crews must manually manage this thick, high-voltage tether. This constant physical connection to the mine's electrical grid means the shovel operates within a strictly defined zone. It is an industrial fixture designed for bulk excavation, not rapid escape. On the night of April 10, 2013, the mountain broke. The northeast wall of the Bingham Canyon mine failed not in a single slide, but in 2 distinct stages. The first collapse came at 9:30 p.m., sending waste rock roaring down the slope. 90 minutes later, at 11:05 p.m., a second failure followed. The material moved with the speed and violence of a rock avalanche, averaging nearly 70 miles per hour and peaking close to 100 miles per hour. Plummeting from a headwall over 1,100 feet high, the debris ran out nearly 2 miles across the pit. In total, between 145 and 165 million tons of rock buried more than 95% of the pit floor. Debris piled between 100 and 400 feet deep. In less than 2 hours, a highly productive mine became a site of historic devastation. Every effort that followed would be a direct response to this single geological event. In November 2012, Kennecott installed an advanced geotechnical monitoring network across the northeast high wall of the pit. Using a dense network of radar, laser, seismic, and GPS sensors, engineers tracked slope deformation down to fractions of an inch. For months, this multi-layered system gathered continuous baseline data, mapping the mountain's minute structural shifts. On the morning of April 10, 2013, the sensors registered a critical shift as the rate of wall movement surged to 2 inches per day. Recognizing the threat, mine managers issued a site-wide warning and initiated a full evacuation at 11 a.m. By the time the first slide struck that night, roughly 350 night shift workers and contractors had been safely cleared from the lower pit. Reflecting on the evacuation, Operations Readiness Leader Ted Heimbaugh noted that although the slide traveled further into the bottom than anyone had planned for, the safety systems worked flawlessly. Because of this precise instrumentation and rapid operational response, a historic geological collapse resulted in 0 injuries and 0 fatalities. Safety systems are central to this recovery story, demonstrating how industrial preparation turned a potential catastrophe into a survival story. In the aftermath of the collapse, viral online claims reported that 14 Caterpillar haul trucks were buried and destroyed. The mine's official records tell a different story. The buried haulers were actually Komatsu 930E 320-ton class trucks. The total inventory of damaged machinery included 13 to 14 of the mine's 100 haul trucks, 3 of its 13 electric shovels, and an assortment of support drills, dozers, and graders. This equipment had not been abandoned in panic. Mine planners had deliberately parked the fleet in a geologist-modeled safe zone on the pit floor, positioning the machines to immediately clear the slide from below once the slope stabilized. However, the sheer momentum of the rock avalanche overrode the simulation. As Operations Readiness Leader Ted Heimbaugh later noted, the debris ran further into the bottom of the pit than the team had planned for, burying the staged fleet under millions of tons of rock. Setting the record straight on this lost inventory clarifies the starting point of the recovery, as engineers now faced a buried fleet. Reclaiming the pit floor required a disciplined, staged campaign rather than a single dramatic pull. Recovery crews described the grueling physical process as modern-day heavy metal archaeology, an operation where high-value heavy machinery had to be carefully excavated from the compacted landslide debris. To free a single buried shovel weighing about 3.4 million pounds, engineers could not rely on simple towing methods. Instead, they designed a coordinated push-pull system that applied an estimated 10,000 horsepower of tractive force directly to the stuck machine. 5 large dozers pushed from behind, while 2 haul trucks pulled from the front, their engines working in perfect synchronization to break the immense suction of the rock. This systematic salvage effort eventually recovered 16 major pieces of heavy machinery. The operation proved that functional recovery was possible. Crews successfully exhumed one of the buried electric shovels, fully refurbished its massive frame, and returned it to active service on the pit floor. But the mountain did not surrender everything. A second buried shovel was declared a total loss and remained entombed in the debris for years. This sustained salvage campaign showed that restoring the mine's capabilities required immense physical coordination, proving that raw power alone was not enough to defeat the slide. Ore processing at Bingham Canyon resumed just 17 days after the landslide. Because the mine's essential in-pit crusher and 5-mile conveyor belt survived the slide intact, Kennecott could bypass the buried pit floor entirely, utilizing existing stockpiles to keep the concentrator mill running. But the financial stakes of the disaster remained staggering. Replacing a single P&H 4100 electric shovel costs approximately $45 million, while each lost Komatsu 930E haul truck carries a $5 million price tag. With the mine losing an estimated $5 million in revenue every single day that ore could not reach the mill, parent company Rio Tinto filed a combined property damage and business interruption insurance claim totaling nearly $1.5 billion. To sustain the massive waste rock stripping program required to stabilize the canyon walls, the company purchased, shipped, and assembled an entirely new shovel in an accelerated 90-day window. Together with this new asset, the successfully exhumed and rebuilt Shovel 99 went straight back to work. Today, Shovel 99 remains an active, primary asset in the Bingham Canyon fleet, still clawing copper ore from the deep pit floor. Today, Shovel 99 still moves mountains in Bingham Canyon. It stands as a silent reminder that no matter how violently the Earth shifts, human engineering matches its scale. We do not just survive disasters, we dig our way out. Share your thoughts in the comments.